Yeah, I was not hearing. I think my name was muted until I saw the text. That is when I discovered you are talking to us. Okay, so let's start. We are still looking at groups, and then tomorrow we look at homomorphisms, homomorphic groups. But today we're still looking at groups. So we began looking at subgroups. Want today to look at subgroups of direct products. Now, so tomorrow we are not looking at homomorphic groups. It's on Thursday that we're looking at homomorphic groups. Tomorrow we'll continue with this subject of subgroups of direct products. Now, so we begin with the direct product where the groups are both additive. Where the groups are both additive. So tomorrow we'll try and see what about if we have one additive group and a multiplicative group, a direct product of that. We'll also look at what if they're both multiplicative groups. So, of course, the techniques of getting subgroups here will differ, and that is why we do them separately. But we learn one technique and understand it, and then come up with a code, and then proceed to another technique. Now, so of course, last week we looked at how to get subgroups of individual groups. So suppose we have this additive group, we learned how to get the subgroups. So what we then be doing, the technique I'm using here is where I get the subgroup for this group and then get the subgroup for this group and then get the direct product of those subgroups. That's the technique I'm using. So of course we know how to get subgroups of individual groups, and we'll again be revisiting as we do examples. Now, up to now, we already know am I still sharing? Can you still see what I'm sharing?
Yes.
Okay. So up to now, we know what cyclic groups are, and we know that the groups we're talking about here, this group is cyclic, and this group is cyclic. And we talked of if the direct product is to be cyclic, then we talked of looking at the M and N. Look at the order of the groups, the order of this group and the order of this group. And we say that if the orders are relatively prime, then the direct product will also be cyclic. But at this time, we know that the individual groups we're considering here are both cyclic. Additive groups, mod N, additive groups, mod N, are always cyclic. What we said is that multiplicative groups, mod N, are not always cyclic. And we looked at when are they cyclic. We looked at this and then said, when are they cyclic? But for this Zn, we said they're always cyclic. And that is why I say subgroups of direct products of two cyclic groups, a product of two cyclic groups. So we agree then that these two are both cyclic. And so we are getting the groups, the subgroups. Now, so I've said that the procedure I'll use to get the subgroups here is to first of all generate the subgroups of the first group, then the subgroups of the second group, then combine those two elements, just the same way we always combine elements of to get direct product. The same way we do get the direct product, the same way we're doing. So first of all, we get the subgroup of this, then the subgroup of this, and then get the direct product of those subgroups. So that is why I said, if you did not remember how you're getting subgroups of individual groups, then again, as we proceed with these examples, you be careful, you be keen so that this time around you get it, how we get subgroups. Now look at the first example. The first example, we've been given this group, which is cyclic, and this other group, an additive group again, and we are asked to get the subgroups of this one group, the subgroups of this one group. So our procedure, and that is how we will write the code, that first of all, we will write a code to give our subgroup of the first group, and then a subgroup of the second group, and then get one that will be combining those two elements. Now, so how do we say we would be getting subgroups of a group Z2 or Zn? We said that we would first of all identify elements which are relatively prime to n, elements which are relatively prime to n. And for this case, the only element relatively prime to n and less than 2 is 1. And of course, we know what this group is, what this set. This set is 0, 1. That set is 0, 1. Now, so the element that's relatively prime to 2 is 1. So how do we use it? We said that after we've identified this element, we would then, since we are dealing with an additive group, we'll then add it several times to generate the elements of this group. We'll add it several times to generate the elements of this group. So when we add it once, you just have 1. When we add it twice, you have 0. So that means one subgroup is therefore 0, 1. That is one subgroup. Now, there's the only element that is relatively prime to 2 is this, is 1. So it generates, 1 generates this subgroup. 1 generates this subgroup. Now, so what is the other subgroup? The other subgroup, we said after the elements which are relatively prime to n have been considered, after all of them have been considered, we then consider the subgroup comprising of the identity and the subgroup consisting of the entire group. But it happens for this case that this subgroup that we obtained is this. So we don't repeat subgroups. That means this set or this group has 2 subgroups, this and that. Those are the subgroups. Now, so what about this one? What are the subgroups? So first of all, what is the group? The group is this, comprising of the elements 0, 1, 2. So that is the group. Now, what elements are relatively prime to 3? What elements are relatively prime to 3? So the elements that are relatively prime to 3 are these 2, 1 and 2. So now, consider each of them, add each of them several times, and generate a subgroup. Let's begin with 1. 1 to add 1 several times and generate a subgroup. 1 once, twice. When you add 1, 2 times. And when you add 1, 3 times, this is what you get. So this is, if you just rearrange, there's no need of rearranging, but just to make it easier for reading so that you can easily read, is easier we arrange, but it is not a must. So this is the subgroup generated by 1. What about the one generated by 2? What about the one generated by 2? So 2 once, 2 twice is 4, and we are talking of mode 3. Mode 3, 4 mode 3. and then add 2 again to this one, and you have 0. So of course, this is the same subgroup that we already have above. So we don't need to repeat it. We don't need to repeat it. So what is the other subgroup? After considering all the elements relatively prime to n, the other subgroup that remains to be added is the one consisting of the identity and then the entire group, which is 0, 1, 2. But the entire group, we already have it. We already have it, so you cannot add it. So the only thing that we're supposed to add is this. So these are the 2 subgroups. Now, so that's what we said. That's what we said. That our procedure will be, first of all, to get the subgroups of each of the groups. The subgroups of each of the groups. And then after that, get the direct product of them. And of course, I take this chance again to remind you how we're getting the direct product. Supposing you've forgotten again, I remind you how we're getting direct product, because that's what I want to do now. That's what I want to do, get the direct product of those groups. Of course, I'll be considering each of them. Now, so the direct product, how do we do it? That means I get the product of this and that. So the product of these two, 0 and 0, the product of these two, of course, becomes 0, 0. Becomes 0, 0. Whereas this 0 is coming from the first group, and this 0 is from the second group. The first group is this, and the second group is this. So we have this. This, therefore, is a subgroup. So I've used, let me use brackets indicating that it's a subgroup. Brackets indicating that it's a subgroup. Now, that is a subgroup, the first subgroup. So I've considered 0 and this. Now I consider 0 with this other subgroup. I consider this, okay, let me say, I consider this subgroup and this subgroup. I now want to consider this subgroup and this subgroup. So I get the direct product, 0, and this other subgroup is 0, 1, 2. Now, so when you get this, what do you get? That is a bracket, just to ensure that I'm talking about a subgroup. It will be 0 and 0, and then 0 and 1. And of course, the order is very important. 0 is on the left. So 0 is on the left. And then 0 and 2. This is another subgroup. So our first subgroup, our second subgroup. Remember, we're getting subgroups to this group. We're getting subgroups to this group. The first subgroup, that group is this, the one consisting of the identity element. And then the other subgroup is this, the entire thing we are seeing here is a subgroup to this. Now, we've considered 0 with each of these. It's now time to consider this subgroup with each of these again, just doing direct product. So when you do that, so you have 0, 1, this subgroup with 0. Now, so I'm just combining 0 and 0, combining 0 and 0, and then combining 0 and 1. So when you do that, you have 0, 0, then 0, 1. No, 0 is on the right. 0 is on the right, so it's 1, 0. 1, 0. So that is a subgroup when you combine this subgroup with this subgroup. It's now time to combine this and this. So let me just create some space here. So I now combine, this one is on the left. Z2 was on the left, so 0, 1 is on the left. And then the other one is 0, 1, 2. Now, so what I'll get is just one subgroup. So I combine 0 with each of them, then combine 1 with each of them. Combine 0 with each of them, combine 1 with each of them. So 0 and 0, 0 and 1, 0 and 2. I'm done with 0. So let me do 1 with each of them. 1, remember, is on the left side. Then 1 with 1. Then 1 with the 2. Then close the bracket. So those are the subgroups of our direct product. And that is the procedure we use to write the code. So the code must then have a function to find the groups, the subgroups of the individual groups, the subgroups of the individual groups. Of course, the individual groups are both additive, so that requires only one function to do that. You don't require two functions for each of them. But if we would have had an additive group combined with a multiplicative group, then we would have had a function, first of all, to do the additive, another one to do the multiplicative. But if in this case, our groups are both additive, so we only require one function to do those subgroups. And of course, you may want to have a, if you want to separate, you may want to have a function that will be giving you the elements relatively prime to n if you want to separate, but of course you can combine one function to perform all those functions. Now, so we'll have a function to do that. And then we'll have a function to do what we've just been doing here, combining those subgroups. Let's look at another example. You recall that this group was not cyclic. Although this is cyclic and this is cyclic, the product is not cyclic because the orders are not relatively prime. The orders are not relatively prime. So I'm just reminding you what we were doing. But in the example above, the direct product is cyclic, this one. The direct product is cyclic because you can see the order of this group is 2. The order of this group is 3. 2 and 3 are relatively prime. Therefore, the direct product is cyclic. Now, so let's come back to the question. The question was, what are the subgroups of this group? What are the subgroups of this group? So first of all, we find the subgroup of each of them. We had already done this in the previous question. The subgroup, of course, of this was this and that. Now, so we have two groups. Each of them, this is the subgroup. So let me just say, and again, I'm just repeating the same. Just repeating the same, so that my calculation, it can easily be followed. Now, so what we did is, after we've identified that the subgroups of the first group is this, and the subgroup of the second group is that, we do direct product of this subgroup with each of these. So 0 with 0 is what I've done here. It gives you that. Gives you that. And then 0 with this subgroup with this. So it will be 0 with the 0, then 0 with the 1. 0 with the 0, then 0 with the 1. When you combine, and you get this subgroup. So we've gotten this subgroup, and we've gotten this subgroup. Now it's now time to combine this with each of these. So 0 with 0, then 1 with 0. 0 with 0, then 1 with 0. This is what you get. This 0 with that 0, then this 1 with this 0. Get the subgroup. And then lastly, combine this with this. So you begin with the first one, first of all, you begin the first subgroup. We've done that. We've done that. So what is left is this and this, the last one, the last subgroup. So 0 with the 0, then 0 with the 1. 1 with the 0, then 1 with the 1. So this is what you have. 0 with the 0, then 0 with the 1. 1 with the 0, then 1 with the 1. So you get those subgroups. So those are the subgroups. Of course, when we were defining subgroups, we said that they must fulfill the axioms of a group. So when you test each of these subgroups you've obtained, you'll discover that they are indeed groups. They must fulfill axioms of a group. So when you test them, you'll confirm that they are indeed groups. They fulfill those axioms. Now let's do the last example so that we now go to the code and apply the same skills. Now, this group, Z4, is the group comprising of 0, 1, 2, 3. The elements relatively prime to 4, the elements are relatively prime. These are the elements which will give us subgroups. That is why I'm considering them. Those are the elements which will give us, we call them proper subgroups. They are the elements which will give us proper subgroups. So 1 is one of them, and then 3 is the other. 1 and 3 are relatively prime to 4. The first subgroup generated by 1, we add 1 several times until we get the identity. The identity is 0. 1 once, 1 twice, 1 thrice, 1 4 times. And if you want, you can rearrange. You can rearrange if you want. It's not always a must, but it's just good manners to ensure that it's easy to read the subgroup without having to check where the element is. So like this one, you cannot even tell if an element is missing. But for this one, it's easy to tell if an element is missing. Now, so what about 3? What subgroup is generated by 3? 3 once, 3 twice would be 6 mod 4. And then, yes, it will be 6 mod 4, because we are doing it mod 4. And then 3 again, that would be 1 mod 4. Of course, it will have been 5, but mod 4. Then add another 3, that gives us 0. Of course, you can rearrange this to be 0, 1, 2, 3, and realize that these two subgroups are of course the same. So we don't need to have all of them. We only require 1. Now, after getting subgroups generated by the elements which are relatively prime to n, the other subgroup that is left is the one of the identity, and the other one is the entire group. The entire group. And of course, you'll notice that the entire group is already included. So that means, therefore, it appears there's somewhere we've not added properly. I think there's somewhere we've not added properly. Because I'm saying, how did I get this? How did I get that? Let's repeat this of 3. Let's repeat this of 3 and see whether what I have here is the one which is wrong or the one which is correct. Let's try this of 3 again. 3 ones should be 3. If I add another 3 there, it will be 4. No, it will be 6. More the 4, that will be 2. That will be 2. Then add 3, I'll have 1. Then add, so why did I write this one here? I think this was a mistake. I don't know how I did it when I was doing it, how I got it. Because the only elements which are relatively prime to 4 are 1 and 3. Okay. That means the end result to then have not be correct. What about this one? This one, you had already done it. You had already done it in our previous example, and we have this. We have that in our previous example. Now, so this is what brings a problem here among my results. But now, so if you want to get the subgroup, the subgroup would have each of the subgroups multiplied by each of these again. So like 0 and 0. Would give us 0, 0. That's what we have. Then 0 with this, 0 with this. So 0 with the first 0, 0, 0. Then 0 with this 1, 0, 1. Then 0 with this 2, 0, 2. So that is how we get this. So let me skip this and just come to this. And then now this on the left and each of this, 0 and 0, you have 0, 0. 0 and now when you come here, just open one bracket and all the multiplications are done inside. Maybe 0 with the 0, then 0 with the 1, then 0 with the 2. Then come to 1 with the 0, then 1 with the 1, then 1 with the 2. Then now come to 2. You have 2 with the 0. So I have this. Oh, this subgroup is, I think it's down here. It's the one down here. Down here. So I have 0 with 0, 0 with 1, 0 with 2, then 1 with 0, 1 with 1, then 1 with 2, then 2 with 0, 2 with 1, and 2 with 2, then 3 with 0, 3 with 1, and 3 with 2. That's another subgroup. Of course, you realize that this is the entire group. This will be the entire group. Of course, it's a subgroup, but again, this is the entire group. The entire group is always a subgroup of itself. It's the entire group. You know, the entire group for this, how do we get the entire group? just remind us how we get the entire group, the direct product. To get the direct product of this, direct product, I'm not talking about the subgroup. Subgroup, we've already done that. The direct product of this, what we normally do, we get this group. This group is 0, 1, 2, 3. And then this other group is 0, 1, 2. And then we just combine the same way we've been doing. 0 with 1, not 0 with 0, will give us this. Will give us this. Then 0 with 1 will give us this. And then 0 with the 2 will give us this. And then 1 with the 0 will give us that. 1 with 1 will give us that. Then 1 with the 2 will give us that. Then come to 3. 3 with, no, 2. 2 with 0, give us that. 2 with 1, give us that. 2 with the 2, give us this. Then 3 with the 0, give us this. 3 with the 1, give us that. Then 3 with the 2, give us this. So that's how we get the direct product. Just reminding us, for those who may have forgotten, how we're getting the direct product, so that you can see that the entire group is always included as a subgroup. So of course we didn't put it here. We didn't have it, but through the calculations, it just came out itself. Through the calculations, it came out itself. Now, so that is how we then write the code, and I want us to look at how to write the code. That means we must have those functions. One function will be giving us the subgroups of each of the groups involved. Then the other function will be giving us the direct product of those subgroups, so that we now come up with the subgroups of the direct product. Okay. Now I've just repeated what we've already said. We've said to effectively produce subgroups, the program takes advantage of cyclic structure of the group. So that's what so cyclic structure, that means that we have generators of, that's what it means. We have generators. So in other words, we would have the subgroups of this generated by elements which are relative prime to this, and then subgroups of this generated by elements which are relative prime to that, and then I get the direct product. Now I said we would get divisors. What are divisors? Elements which can divide n. Elements who can divide n. Elements who can divide m. We need that. Then we need this function to generate subgroups. Hash set to ensure that there are no repetitions, there are no duplicates. And then we have this, generate all subgroups. Generate all subgroups. So this will be generating one subgroup at a time on request by this. So this one requests a subgroup to be generated, then this one generates that subgroup. This one generates, this function generates. So this is one will be requesting. You can see the request it's making here. Look at this request. Look at this request. It's saying generate a subgroup with the n and a certain generator. So it has given a generator. It gives this specific generator. It sends that generator to this. So this one, using that same generator, coming from this function, it comes up with a subgroup. Comes up with a subgroup. Then after it has come up with a subgroup, this one takes this subgroup, and it has said here, push. Why is it pushing it? It's pushing it here. Inside this empty vector. What is this? This is subgroups. Subgroups. So that is where the subgroups are being pushed. So once this one calculates the subgroup generated by a certain generator, that subgroup is pushed here. That's why it's pushed. So the first function was divisors, come up with numbers which divide n and divide m. Those will assist us get the generators. Then this will be generating one subgroup at a time on request. On request. So if this one requests for that subgroup, it provides the generator it wants the subgroup to be for. Then this generates. This one generates. And then, so this one is what is happening here? So this one is generating subgroups for Zn. Also generate subgroups for Zm. And this one will now, from here, get the subgroups of Zn and get those of Zm and combine. So this is the one which will be combining. Should be doing that direct product. The main function is just waiting, actually. It's waiting. It has a few functions that be doing. Then the main one is now to print the result. Okay, I want to show you how they work. And then we go to the code. You look at the code. But let's first of all understand how it's working. Of course, I've given a skeleton view of what will be happening. The whole thing begins from here. The main function. I want Zn, the subgroups for Z4 or Z3. Want the subgroups for that. So I enter 4 and 3, this point. When you enter that, this main function calls on generate all subgroups product. Generate all subgroups product, NM function. Calls for this function. What is that function? Generate all subgroups product. Generate all subgroups product. Is this. So it's asking this function to generate all subgroups for the product. Now, this one does not have that ability. So what it does, it calls on the subgroup of Zn. Calls on this function to do that. Calls on that function. Generate all subgroups of Zn. Then it calls on the same function again. Generate all subgroups of Zm. Also on the same. So once it has those two, it can do what the main function required it to do. Where is this function that has been called upon? So that is how it's moving. So this function has been called upon to do that and provide. It's here. Generate all subgroups. Generate all subgroups. But it doesn't have that ability. It doesn't have ability to generate all these subgroups on its own. It has to call on some other function to assist it. So it wants to call on this subgroup, on this function. But before it calls on it, it gives it a generator. It gives it a generator. So for instance, it can give it a generator like 3. Give me the subgroup generated by 3. Now, how is the generator defined? To get the generator is going to the first one, which is divisors. Divisors function. And then gets the divisors. Gets the divisors of n and comes here. The generator will be n over the divisor. N over the divisor. So after it gets that divisor, suppose that divisor is, supposing this generator is 3, n over divisor, supposing it's 3, it now requests for this function to get the subgroup generated by 3. And so why is that? This is what is being called on. So you can see how the process is going from the main function, how we are moving up to the start. So this one has been called upon. And of course, the divisors has also been called upon to provide the divisors of n. So let's see what this one is doing. This one, using those divisors, is generating each of the subgroup requested. So this is where most of the work is. This is where most of the work is. And of course, this part. Let's begin with the first part, divisors. See what it's doing as we move down up to the main function. Because now after the main function calls, and then it comes here and then again moves down to the main function until it's printed. This one wants to the divisors of n. It says, let those divisors be mutable. And then it opens an empty vector where it be storing the divisors. Supposing we have 8 as our n. Supposing 8 is our n, or let's use 4 in this case. Let's use 4. Now, it knows that we have Z, when you talk of Z4, it knows that we are talking of values 0, 1, 2, 3. That is why it has written here. For I, from 1 to n, where it understands that when we talk of 1 to n, it understands we are referring to 1, 2, 3. So it has omitted this. It has omitted this because this is not a divisor. Can't be a divisor. So the divisors will just be 1, 2, one of the numbers among this, will be among this. 0 cannot be a divisor. So it's saying for I from 1 to n. So for I from 1 to 3, for instance, 1 to 4, where it understands that it will be 1, 2, 3. It wants to find the divisors of 4 here. So it says for this I, then you enter the loop. If n divided by I will give a remainder of 0, then this I becomes a divisor and is pushed inside that vector. So for instance, 4 divided by I, where I is 1, gives you a remainder of 0. So therefore, 1 is a divisor and is pushed there. What about 2? It gives a remainder of 0, and therefore 2 is a divisor and is pushed there. What about 3? Is not equal to 0. Is not equal to 0. is not equal to 0. So it's not pushed there. So at the end of the day, we have the divisors now, 1 and 2. We have 1 and 2. Now, so this one calls, this one is the one which will be calling the divisor. For a certain divisor, it requires a subgroup for a certain divisor. No, a certain generator. For a certain generator, it requires a divisor and so on. So what is it doing here? It begins by saying, let the subgroups be mutable. Opens an empty vector for storage. For the divisor D in the divisors above, for the divisor D, for D in the divisor above, for D in the, for instance, I can say for 1 in the divisors above, for 1, because we found the divisors there to be 1 and 2. So it says for 1 in the divisors above, then come inside here. Let the generator be n over 1. Let the generator be n over 1. So it's asking when the generator is 4, therefore. So this is how it does. And then it says, let the subgroup be, then it calls on this function. Generate the subgroup where the generator is 4. Generate a subgroup where the generator is 4, and then it waits. It waits for that subgroup to come. When it comes, it pushes it here. So this definitely, this is what this will be doing. So it has done for when it is 1, then after it receives that subgroup, it requests for when it is 2. When it is 2, it requests for another subgroup, and so on. So that is how this part will be working. So of course, this one doesn't have a lot of calculations here. It's just requesting. What about now the one being requested? The one being requested is here. Generate subgroup. Let us see how it will be working. It has been given a generator to use it to generate a subgroup. Now the generator it has been given is 4. It has been given 4 as the generator. N is 4, and the generator is 4. It's supposed to generate a subgroup. It says, let the subgroup be mutable. Hash set, then it opens a new vector, empty. Hash set, we said, is just to ensure that once a subgroup has been stored here, another subgroup, the same as which has been stored, does not come in. We do not have duplicates. So it's just to ensure that there be no duplicates. Once a subgroup has been stored, there is no allowance for a similar subgroup coming in. Now, so it says, let the current be mutable. Let the current be mutable and initializes the current at 0. So the subgroup is mutable, opens an empty vector, then let the current be 0. It's also mutable, be changing. Then the loop. While the subgroup does not contain the current, while the subgroup does not contain the current, insert the current and then rework the current. So you come up with a new current. Insert that new current, the old current, then work out the new current. So let's do how it will do it therefore. It has received 4 as a generator, and n is 4. Opens that, then let the current be 0. While the subgroup does not contain the current, of course, this is the subgroup, this vector here. Does it contain 0? It doesn't, because it's still empty. It's still empty, so it does not contain 0. So insert the current. So that means this 0 should be inserted there. That's how we begin. So we've inserted 0. Then after inserting 0, what does the current become? The current become the old current, which was 0, plus the generator, which is 4, the result divided by n, which is 4, and then you write the remainder. This is our new current. What is said here? They say, while the subgroup does not contain the current, insert the current. But our current is 0. And this subgroup already contains 0. So we cannot insert it. We cannot insert it there because it's already there. So that means we exit with 0 as the subgroup. We exit with 0 as the subgroup. So that means 4 would generate 0. Subgroup containing 0. Okay, what about if n is 3 and the generator is 1? What about if n is 3 and the generator is 1, and we want the subgroup corresponding to that generator? So it will again do the same thing. It will say let the subgroup be mutable and open the new vector. Of course, there's hash set. Let the current be 0. So I begin with 0. Of course, this is empty, so it does not contain 0. So this part is true. While the subgroup does not contain the current, insert the current in the subgroup. We insert the current inside the subgroup. So we insert 0 here. So we have 0. And then after getting 0, rework the current. So the new current, therefore, is the old current plus the generator divided by n, and the remainder will be 1. That is now our new current. And then what does this one say? While the subgroup does not contain the current, insert the current inside that subgroup, inside the current. So our current is inserted there. Because it was not there, so we insert it. Since we've inserted, we calculate the new current. The new current will be the old current plus the generator divided by 3, and of course the remainder is 2. This is our new current, now 2. We come here. While the subgroup does not contain the current, this is now a current. Is it contained here? It's not. What does it say? Insert this current inside the subgroup. Because it's not there, so we insert it. After inserting, we work the new current. The new current will be the old current plus the generator, the result divided by 3, and the remainder is 0. The remainder is 0. Okay, we come here. While the subgroup does not contain the current, insert the current. This our current is already inside the subgroup, so we can never insert it again. That means we close the bracket and exit the loop. So we exit the loop with this subgroup. We exit the loop with that subgroup. So those are the subgroups we were getting at that time. So that's how we do it. So you exited the, so once this you exit the loop, the function down here, the function that required the subgroup takes it. One that required the subgroup takes it and then pushes it into the empty vector. So the subgroup that wanted it, the one that I'm referring to, is this. This is a function that had requested for the subgroup. So once it gets that subgroup, pushes it inside that vector. It will ask for all the subgroups using all the generators, and then after that, it will come up with all the subgroups for Zn. Then again, it will ask for all of Zm, come up with all of them, and again, have all of them because they are required, they were asked for. They were asked for by this function, this one. This is the one which required the subgroups for Zn and the subgroups for Zm. So how is it going to use it? How is it going to use those subgroups? It has received them. So how is it going to use them to get this? It begins by saying, so it calls for those subgroups. So they come, those subgroups come for Zn. Then it calls for these subgroups. Then they're also provided. So it has those two subgroups provided. Now it wants to get now the direct product. Supposing it got the subgroups here as 0, that, and then 0, 2, then let me say 0, 1, 2, 3. Supposing it got those. And supposing here it got 0, then got 0, 1, 2. Supposing those are the subgroups. Now it has them. How does it use them to get the direct product? It says, let mute the direct product of the subgroups. Let them be mutable. Let the direct product of the subgroups be mutable, and then open an empty vector. For the subgroups in N, this Zn, the subgroups for Zn, now it's considering those subgroups for Zn, the subgroups from Zn, the one it's considering. And then for the subgroups from Zm, it's also considering those. So for these subgroups and these subgroups, for these subgroups and these subgroups, let the direct product be this empty, and of course, hash set to ensure that there be no repetition. For A in this Zn, so what is referring to is each of the subgroups. These are the subgroups for Zn. So it's referring to this part is calling it A, or this one A, or this one A. So each of the subgroups, respective subgroups in Zn, are referred to as A. So for A in Zn and for B in Zm, so again, it's referring to this as B and this also as B. So each of the subgroups here are referred to as B. Now, so for A in Zn and for B in that, it combines, just takes A and B. Just takes A and B. And then pushes that the element received there, pushes it into this hash set, new vector. Of course, after pushing it, it also pushes it here, and then pushes it there. So we said that the why it's pushing it here and pushing it there at the same time, in both cases, this part is not very necessary, but it was just to ensure that there be no repetition. Just to ensure that there be no repetition of those subgroups. You could omit it, but when you omit it, then you will get repetitions. There'll be duplicates. So its only role is to ensure that there are no duplicates. Otherwise, if we would come up with another way of ensuring there are no duplicates, we would omit it. We really don't require it, not a mandatory there, but for the sake of ensuring that there are no duplicates, and then we have it. So it's just combining those elements, the way we did with our examples. Okay, so let me show you how the code works. Okay, let me show you this. Oh, I stopped screen sharing. I was sharing. Oh, just a minute. Let me open it again. Okay, here it is. So let me share it. Am I sharing anything?
Yes.
You can see
your code. Yes.
Okay, okay. There's something I wanted to minimize here, and when I try to minimize, I closed the code. But I wanted to minimize the list of the participants so that I can enlarge. I don't know how I usually minimize it. This time, the icon for minimizing is hidden inside this add-on. But you can see it clearly.
Yes.
Okay. So the part for the generator, no, the part for the devices, function for the devices is this one. Then we have the function for generate subgroups. So it'll be generating each subgroup corresponding to each device generator as requested. Then the one that is requesting is this function, requesting for a certain subgroup, and then provides the generator whose subgroup it requires. Then after it obtains all the subgroups, this one requires those subgroups for Zn and the subgroups for Zm to get their direct product. And then after that, what requires that is the main function. The main function requires those direct product subgroups so that it can print them. So let's just try to run this. It then gives us the subgroups, of course, arranging them so that the main group, the entire group is at the bottom, begins with the identity element, and then not necessarily in the order of their sizes, but in the order of the generators. The order of the subgroups, as it multiplies the subgroups. As it multiplies the subgroups, so the first subgroup with the first subgroup on the right, the first subgroup with the second subgroup on the right, and so on. So that's how it does. Let's just try to change the sizes and see what we get. So we get several subgroups here. Of course, I don't want to use very big numbers because you can get several subgroups until you cannot see where it begins and then ends. Like for this one, this case, this subgroup that I'm highlighting begins and then ends here. You can see it's 2 lines. It's 2 lines. So if you have a case where one subgroup is 5 lines, you cannot even be able to see the other subgroups. That's why I just want to stick on the smaller. Like this one begins and ends there. This one begins and ends here. What about this one? Where does it begin? The one I'm highlighting. I want to see where it begins. It appears like it begins here. It begins, there are 3 lines. It begins with the 0, 0, 0, 1, 0, 2, and it goes up to 7, 4. You can see that's a long subgroup. And we've only used 8 and 5. That means if you use 10 and 15, for instance, you expect one very long subgroup so that you may not be able to see the rest. The cargo TOML, I do not have anything. We don't require dependencies for this. There are no dependencies required for that. Of course, if you wanted to deal with the very big numbers, then you will have dependencies. You'll be using some libraries again. The only library I'm using for this case is just hash set that ensures that there are no duplicates. It's the only library I'm using. But if you wanted to use very big groups, bigger than U64 and bigger than U128, then you would require other libraries, and therefore you will require some dependencies to assist you in doing that. Now, so that is how we do the code, and I've written all the notes that the ones I was explaining. I've written all of them so that at your own time you can go through, so that where it was not clear in the explanation, you can easily see it, and or where there's some contradiction, you can easily see and correct. This is how it works. So we have this generating all subgroups of Zn. This function generates every subgroup of Zn. It creates a subgroup by using this generator, and then storing that subgroup in the empty vector, this empty vector, storing it there. Then this one requires, first of all, the subgroups of this, then the subgroups of this, then it will be doing the Cartesian product. We're doing direct product of those subgroups. We're doing the Cartesian product, which we also call the direct product of those subgroups. We've seen how that will be happening. Of course, this part is just nothing much is going on here. This part is just requesting for the subgroups of Zn, all of them. Then is asking at this point for the subgroups of Zm, all of them. Then after it has received them, it then comes and tells you how it's going to combine them. Okay, that is how this code works. That's how this code works. Of course, the part of the main function is not a lot. After it has received the subgroups, it will just be printing them. Any question up to there? Okay, then that becomes the end of today's class. Thank you.